Hello everyone, my name is Ahmed Safa and welcome to a new video in SBS channel. Today we're going to talk about a theory that we have been working on. It's like a new theory and it's not proved yet. And we are sharing this theory with you so you can give us ideas how to prove it or how to improve this theory. So what we're gonna do here is divide a circle into 10 parts, where every single part contains a specific type of numbers. It's the type of numbers that ends with the same number. For example, we're gonna put all numbers that ends with the 0 in the part 1, in this part, like 0, 10, 20, 30, and it goes like this. Also, we can put the numbers that ends with 1, 11, 21, 20, 31, and it goes like this. Why I did this? This is so important because when you are looking for patterns, you need to deal with all the numbers. But with this circle, we don't have to. We actually need just to deal with 9 numbers from 0 to 9, because those 9 numbers actually represent all natural other numbers. For example, 2 can represent all the numbers that ends with 2, 22, 32, 42, and it goes like this. We can represent multiplication tables, all of them, all multiplication tables in this circle, and it's going to give you like a very cool patterns, and these patterns will show in the circle as a special shapes, where every multiplication table, like the 2 multiplication or the 3 multiplication table, every one of them has his unique own shape in the circle. So let's start with 2. I'm going to show you how to do it with 2, and then I'm going to show you the shapes that will appear in the other multiplication table. So let's start with 2. 2 times 0 is 0. 2 times 1 is 2. So we're gonna connect 1 with 2. 2 times 2 is 4. So connect 2 with 4. 2 times 3 is 6. Connect 3 with 6. 2 times 4 is 8. Connect 4 with 8. And continue doing this until we get back to 2 times 10 is 20. So it's still on that point. 2 times 11 is 22. In the same line, and this shape will continue to show up. So that's the shape of these the 2 multiplication table. For the others multiplication table, here is the 3 multiplication table, the 4, 5, 6, 7, and you can continue. You don't have to stop in the 10 multiplication table. You can continue to infinity actually. And this is something really, really cool. So you can connect all prime numbers in this circle, so we can discover what is the pattern of prime numbers. We have 2 is prime number, then 3, then 5, 7, 11, 13, and this pattern will continue to show up every time we connect prime number with the next prime number. To make the picture clear, we can avoid 2 because 2 is the only prime number that really ends with 2. So we can consider it as a special situation. And also we can avoid the number 5 because it's also the only prime number that ends with 5. This pattern here is the pattern of prime numbers. And since this pattern is like a very important pattern, I thought that I should program it and show it better to you. So I programmed a small script using Python, and I used matplotlib library to program this. So here is the code, and it's pretty much not that complicated. And if you want to understand the code, you need to watch the whole video so you can understand the mathematics way that I had used to make this. So let's run this script and see like the real pattern. And this pattern is like really important. That's why I had to make a script. So I'm going to give it a start number. I'm going to give it a 5. As I said before, I can avoid the. I'm going to start with 7. I can avoid the 5 and I can avoid the 2 because they are a special situation. So we're gonna start with 7 and we're gonna end up like let's take a one. Let's take, I don't know, 100,000 numbers from 7 to 100,000. The base is something that we're gonna talk about in the next video, in the part 2, because the base is something that we're gonna use to prove other things. So we're gonna use the base 10. Now I'm going to wait a little bit until the program will check. So yeah, here is the pattern. Here is the prime number pattern. And here is the circle that we have been talking about, and there is the point, and every single point like represents a special kind of numbers and everything. Clearly there is a pattern here. Clearly there is a pattern. And in the second part of this video, we're gonna focus in this point because I believe that this point have something to do with the prime numbers and everything. We're gonna talk about it in the second video. And so yeah, this is the pattern. And actually this program, when I programmed this script, I made it in the way that I can use it to represent like any function. And the only condition is that this function is a function that defined from n to n. I mean from natural numbers to natural numbers. I cannot use real numbers. Even the PC or the computer can understand real numbers and can present it in a circle, but I cannot do that because this theory we are defining it in natural numbers. So back to the board. So what we're gonna do here is connect this circle with a platform that is an X and Y platform. So first let us give like write a mathematical definition to every single part of this theorem, this circle. So numbers that end with 0, like 0 and 10, and you can consider it as a 10k, when k is a natural number. This one over here is 10k plus 1. Here is 10k plus 2, and you can continue doing this. So here's our circle. Now it's ready to start proving. So we're going to consider that this is the x, this is the x-axis, and this here is y-axis. So this over here is an angle. Let's call it where alpha is divided by 10, which is pi divided by 5. We have from the circle, if you can notice, 10k plus 1 is actually equal to exponent of pi divided by 5 multiplied by e, because we can consider this point here as complex number, and we can represent it like this. Also, 10k plus 2 is exponent of 2 pi multiplied 2 pi divided by 5 multiplied by e. We can continue doing this until we find that 1k plus n is equal to exponent of n multiplied by pi divided by 5 multiplied by e, where n is a natural number and n is between 0 and 9. So until now we have this. And this is the first thing. Now we need to find another way how to get the last digit of a number. Like when we have, for example, 105, we will get 5. We need a function that can do that. So let's pretend that I have a natural number, let's call it s. I want to get the last digit of this number. So let's call the last digit n. N is equal to this number minus divided by 10 multiplied by 10. This actually over here, this is, let's call it a function. This function over here will give you the last digit of the number s. It's like really cool. And now we have this. And we also found this one, which is come back to it. So we said that n is equal to 10. Can write s with this way. S is equal to 10k plus n. This came from the fact that s is a natural number. And we can write all the natural numbers 10k plus n, where n is between 0 and 10 and 9, and k is a natural number. So now we have 3 relations, and all what we need to do is connect all of those relations and get one simple relation. We can conclude from this that s is equal to this. And we already said that n is equal to this, so we can put n over here. And finally, we get what we want, which is a relation that can combine a plot, an x and y plot, with our circle. So this relation over here will allow you to represent any number or any function actually in our circle over here. And this is what we got so far. We hope that you will help us finish this and maybe prove something and prove that actually there is a pattern in prime numbers. This is the part 1, and we'll meet you again in part 2. Thank you.